This week we're going to discuss designing for various building functions and creating an ambient environment for human use. Now, most of the stuff we're going to talk about is sort of an introduction for the rest of the semester, where we'll be talking about these various aspects of building functions in more detail. The building envelope is the exterior surface of the building. It includes the wall, floor, ceilings, roof, etc. It encloses the conditioned space. The building envelope can also be called the building shell. It separates the interior from the exterior. Now, it used to be considered an isolated environment, but now it's seen as a dynamic boundary. It means that it serves to link the indoors with the outdoors in a more appropriate way. The two work together. The building envelope should be able to manipulate the resources of the sun, wind, water, etc. to create a comfortable interior environment, transferring thermal energy to or from the outside world. These are some ways that the building envelope can be designed to support the dynamic approach. By letting in or closing out the sun's light and warmth by adding adjustable blinds and shades to windows, using walls when wanting to keep out the exterior environment, adding adjustable doors and windows when wanting to keep the environment in. Here's an example of adjustable fenestration in the Chicago window. The center panel here was fixed, and it was large so that lots of light could come into the building. This is before really electricity and mechanical ventilation. Then the side windows opened and closed to allow air to circulate through the structure. The form and orientation of a building has a direct relationship on how the structure will be protected from and make use of the environment. We talked about this a lot last week. Sustainability is not the only reason, though, we design buildings in specific forms. For example, the Flatiron building here was created into a pie shape to fit on a pie-shaped lot. The Jumeirah Beach Hotel in Dubai was designed in this sail-like fashion mainly so that all of these guest rooms could have a great view of the beach. I'm sure if you've had plenty of studio classes, you know that the bubble diagram is an example of how a designer or an architect begins creating the building form. Spaces with similar needs are grouped together. For example, areas with the need for public access are placed near the ground level typically, and with access to the exterior. Closed areas and mechanical areas can be placed in higher floors and towards the center of the space. Larger buildings are typically separated into two zones, the perimeter zone and the interior zone. The perimeter zones are attached directly to the building envelope and are most affected by the weather outside. The interior zones are more protected from the exterior and may require less heating, but they frequently require more cooling and ventilation. The space that runs between the floor and the ceiling below is called a plenum. The purpose of the space is to move air and house electrical wiring, plumbing, lighting, fire protection, and other important functions of the building. There is typically also a vertical shaft that runs all the equipment in the plenum down to the next level. These are called plumbing, electrical, and mechanical chases. These spaces must be isolated. How you design the interior space of your building or where you locate design elements will depend on the location of the equipment in the plenum. For example, ceiling details have to take into consideration air ducts and the depth of your light fixtures and wiring and those sorts of things. Service areas of a building are generally grouped together in what's called a service core. Included in these areas are the building's stairs and elevators, supply rooms, mechanical rooms, plumbing, electrical, and mechanical chases that run from floor to floor, electrical, telephone, and service closets, and also the bathrooms. The purpose of the service core is to carry these utilities from one floor to the next. It's a lot less expensive to put bathrooms on top of one another so they can share all of the pipes and the vents than it is to place them sporadically throughout a building. The location of the core is very important to the design of the building and you as a designer. You must be conscious of the location of the service core to rentable spaces in the building because it has a direct impact on the safety and the comfort of the occupants. mainly because the bathrooms and the exit access are located in the service core. So codes will tell you how close your interior spaces have to be to the exit access, and you also don't want your tenants walking a mile to go to the bathroom. Now, common service core layouts are those that you see here. We have the central core, or a single core, that's located in the center of the building. This is the most frequently used. It provides the maximum amount of unobstructed rentable area. It also allows for shorter wire and pipe runs and more efficient air distribution. We also have the perimeter service core, located at the exterior of a building. This type of core leaves more unobstructed floor space, but it blocks some of the daylight, obviously, because it's taking up an edge, and requires a longer service run to reach the opposite side of the building. The attached cores that you see there in the center are located outside the building. This type of service core saves on valuable rentable floor space, but also requires long service runs and sort of limits flexibility in how the space can be used. The symmetrical core reduces the length of the service run, but it takes up more floor space. And multiple cores are found in more horizontal buildings or longer buildings with fewer floors. These help avoid really long service runs. How the temperature feels inside a building is based more on factors than the number that is read on a thermostat. The season, the humidity level, the air movement, heat maybe that is radiating off objects nearby. And as our body operates necessary functions for sustaining life, it also creates heat. Ever notice how cold an empty airplane feels, or how hot and stuffy crowded rooms get? This is because of body heat. The average person at rest gives off the same amount of heat as a 70-watt incandescent bulb. This rises to 100 watts when sitting at a desk, 200 watts when walking, and physical activity can skyrocket that up to as much as 870 watts. As designers of interior spaces, our goal is to create environments where people are neither too hot or too cold to function comfortably or efficiently. Now, the surplus heat in our bodies is passed to the environment in 4 ways: through convection, conduction, radiation, and evaporation. With convection, air molecules absorb heat from the body. In conduction, heat is transferred through direct contact with cooler surfaces. Heat radiates to cooler surfaces without physical contact in radiation. And in evaporation, heat is drawn from the body's surface to provide energy to turn liquid water into water vapor. Now, visual comfort applies not only to stunning views and beautiful interiors, but also providing adequate light and avoiding glare. Interior designers should avoid strong contrasts that make vision difficult or painful, like very bright objects against very dark backgrounds, or vice versa. Lighting levels and daylight contrast are important parts of interior design. Interiors should also be planned to provide acoustic comfort, allowing for audible privacy as well as reduced echoing. You don't want people in different rooms hearing each other, but you don't want people in the same room having their voices bounced off the walls to create a lot of loud noise. Other considerations for designing structures that accommodate the human body are water supply for drinking, washing, and carrying away waste, ventilation, which provides clean air to breathe and the removal of airborne toxins, smooth floor surfaces and appropriate space planning that allows for unobstructed and safe travel through the structure, and designs that help suppress or prevent fire and provide safe escape routes from a burning building. So many of these factors are important to human health and safety that government regulates them in enforced building codes. It's important to note, though, that building codes establish minimum acceptable building practices. They're basically a place to start. Now, your book talks about various building code agencies in some more detail, which I encourage you to read. I do realize that you guys take a full class on that, so we won't go into any more of that here in the video. Now let's take a look at a case study. Manassas Park Elementary School, located in Manassas Park, Virginia, was designed by VMDO Architects and completed in 2009. The building functions were designed for maximum human comfort and environmental sustainability. An E-shaped courtyard configuration allows classrooms to face north and south for optimal daylighting. The west face of the school is shaded by a forest. The eastern wall contains minimal fenestration or doors and windows openings to reduce morning heat gain. Thermal comfort was addressed by using glazing with a low solar heat gain coefficient. Visual comfort and energy efficiency were addressed through the incorporation of skylines, skylights, clear stories for daylighting. Artificial lighting is dimmed using daylight sensors, and when in use, each row of light dims to the needed level of illumination. Acoustical comfort was addressed by minimizing sound transmission between rooms using appropriate detailing and material densities, as well as acoustically absorbent materials used on the ceilings to reflect or to lower the reflection of noise levels. And finally, air quality was addressed with a heat recovery ventilation system, which introduces fresh air into the building, but also maintains climate control and improves energy efficiency. It's like being able to open the windows without letting in the heat or the moisture. The earliest structures probably provided only a little shade or protection from rain and were warmed by fire and enclosed by one or more walls. Today we expect a lot from our buildings, beginning with the necessities for supporting human life like clean air to breathe and water to drink. Once these basic physical needs are met, we can then turn to creating conditions for sensory comfort, creating an ambient environment, allowing for efficiency and privacy, sustainability. We need illumination to see and barriers to provide for visual privacy. We look for spaces we can hear others speak clearly, yet where we have also acoustic privacy. The next group of functions that our building offers supports social needs. We try to control the entry or exit of other people and animals. Buildings facilitate communication and connection with the world outside through windows or even telephones, mailboxes, computer, video networks. Our buildings support our activities by distributing concentrated energy to convenient locations, primarily through electrical systems. Allow us to plug in our laptop, get our Wi-Fi, etc. Then the structure of the building provides stable support for its architectural features and all the people and objects inside it. The structure resists the forces of snow, wind, and earthquakes, creates a dynamic boundary between the interior and the exterior, supports our comfort, safety, productive activity with floors, walls, stairs, shelves, countertops, and other built-in elements. And finally, the building capable of accomplishing all of these things must be constructed without excessive expense or difficulty. We need to have affordable buildings that can be easily built by most people. Once built, it must be able to be operated, maintained, and changed in a useful and economic manner. Ideally, the building should be flexible enough to adapt to changing uses and priorities, and eventually the building's components may be disassembled and returned to use in other construction or recycled.